Okay, that's our group today. And from next week, I think we're going to fix our group. Okay. I'm going to give you the paper back again. So if you have a change of plan to whom you to be grouped with, then write your group member's name along with your name together. Okay, so let's start. So Bourne's rule, I think this is an interesting topic. So although it's not 100% related to the quantum computing, but the essence of what Bourne's rule says is the core of the quantum computing. So this is actually an animated picture, but in the PDF file, it doesn't move. But anyway, so I want to talk about the measurement. The measurement is a process that extracts information from quantum system, and it's by observing the state. So you probably heard about what happens when you observe a quantum state. When you observe something, then it fixes to that state. So it's observed the state. If you and the problem is when you make a measurement, you either observe 0 or 1, up or down, spin case. So whenever we observe it spin up or 0, then the quantum state will be stays that way. So that's called collapsing. So Bohr's rule is simple. So if you have a quantum state as a superposed state of ket 0 and ket 1, and the coefficient or the strength of each state is alpha and beta, then the probability of observing 0 is alpha absolute value square, and probability of observing 1 is beta absolute value square. So the statement is simple, but if you think about the meaning of the statement, then it becomes a little bit quite weird. So you either observe 0 or 1. There's no going back, okay? So there's no going back and measure the same qubit again. But still says there is a probability. So what does that mean? So it only means in a mathematical sense that if you have such quantum state like this one, then when you have 50% chance of observing 0 and 50% chance of observing 1. So it doesn't determine your observation, it just gives you the probability of your observation. You can mimic the Bohr's rule by preparing a quantum states, many quantum states, like thousands of quantum states, assuming that every quantum states are in this state, and you take the measurement, that means approximately 500 observation will be turned out to be 0, and approximately 500 observation will turn out to be 1. And that's all. It's not about a single qubit. It's a probabilistic story. And here's a generalized Bohr's rule. So whenever you have an n qubit state, assuming that there are, n qubit information in a system like n quantum material, and it's actually n plus 1 here. And you know that it's a superposed state of these two n plus 1 states. So this is n plus first qubit state, and the one on the right is n qubit states for n qubits. Okay, so don't confuse by the order and the label of the qubits. So there are n plus 1 qubit, the labels start from 0 to n, and the first n from 0 to n minus 1 gives you the state of phi 0 and phi 1. But the last one, the n plus first qubit, labeled by n, is now either 0 or 1. So when you take a measurement on the qubit n, which is n plus first qubit, and it turns out to be 0, then you had a probability of this much. So you had a lock that have a probability of getting absolute value of alpha square. And what happens to the rest of the qubit, the first n qubit, is that the state of rest of the qubit are going to be collapsed to phi 0. Okay, so you by measurement of the n plus first qubit, you kill this superposed state. Okay. Now let's have an example here. Let's try to find out the probability of observing 0 or 1 on the qubit 0 for the following state. So this is qubit 0, and this is qubit 1, by the way. Okay. So you're going to take an observation of observation on qubit 0. Try to find out the probability of observing 0 or 1. So let's do it together, and then I'll leave these questions to you to work on your own. So how we're going to we are going to break down into two summation here. So there are two states whose qubit 0 is in the cat 0 state. First one is this one and this one. And I'm going to group this together. And then there are quantum state whose qubit 0 is in the cat 1 state, this one. And then let's rewrite this again. So this one, now it's going to be, let's see, 0 tensor product with 10, 0 plus 10, 2. And this one will be 1 tensor product with 10, 3, 0, 10, 2. So my question is, okay, let's suppose that I took the measurement and I observed 0. So then, what will be the state of the remaining qubit? What will be the state of qubit 1? Will it be this or something else? So if it's going to be this, then you can see that this is not a uniform state. If you take the strength of this qubit state, it's not 1. Okay, and also if you work on this statement, work on this formula, then what is the probability of observing 0? What is the coefficient here? Is it 1? No, it doesn't make sense, because if it's 1, then it's 100%, but there's also another state here. So you have to determine your coefficient here. What will it be? So you have to normalize the state of the remaining qubit. So this one has a size of 10 plus 1, 4 square root. So basically it's 1 over square root of 2. So you have to normalize it by taking square root and then multiply again. So if you take these things, so nothing changed. I get the same superposed state, but now this is normalized. And now this is my coefficient. And how about this? So if you take 3 plus 2, oh, it's the same thing, right? So we get 1 over square root of 2. So you have a size of 1 over square root of 2. You have to normalize it by multiplying and then remultiplying this. And so this one now is normalized. So you have to imagine that original state is composed into tensor product of two quantum states, and each of these are tensor product of normalized state. So this one, first one, is the normalized state of qubit 1, and this one is normalized state of qubit 0, and same for the rest, another summation. But the difference is that we have different coefficient, like 1/2 on each. So now we can compute the probability of observing 0 or 1. What will be the probability of observing 0 at qubit 0? What is it? The square of the absolute value of alpha. What is alpha here? One over square root of 2. That's alpha. This is alpha. Here, alpha is here. Okay. So what is the probability of observing 0 at qubit 0? 50%. How about how about observing 1? Yes, same 50%, right? So you have 50-50 chance to observe either 1 or 0 when you take the measurement of qubit 0. Now, suppose that you took the outcome is 0. So what will be the state of qubit 1 after measurement? This one, right? The qubit 1 will be fixed to the state of this. So let me rewrite this. So this is 1 over square root of 5, 0 plus 10 square root of 2, right? If I take the size of the strength of this qubit state, let's see, it's a 5 over 1 plus 10, 2. It should be 1. Let's see. Oh, I forgot. This is 2 over 2, right? Yes. So when you take the measurement, when you take the strength of this qubit state, it's 1 over 5 plus 8 over 10. So if you add together this 10 over 10, it's 1. So it's same thing as it's normalized. So now let's take the measurement on the qubit 1. So since we took the measurement on qubit 0 already, it's going to be the qubit 0 is now in the state of ket 0. It's collapsed. But qubit 1 didn't took the measurement, so now still in the superposed state. Let's take the measurement. What's the probability of getting 0 after measurement? 20%, right? So how about 1? 80%, right? So you have, so suppose that now I got this one. So after taking measurement on qubit 0, I observed 0. And after taking measurement on qubit 1, I obtained 1. So that means I have this state, right? This state. So if you considering the probability, the total probability of observing this state, now you have 50% in the beginning, right? And then 80% next. 5 over 4. How many chances that you will observe these outcomes? 40%, right? So this is 40%. And look at this one. So what's the probability of observing 1, 0? 40%, because you take the square of this number, it's 4 over 10. So it's a 40%. The same thing as you think that this measurement is done simultaneously on qubit 0 or 1, or you can take the measurement in sequel. First qubit 0, and assuming that qubit 1 is collapsed to a certain state, and then take the measurement on qubit 1. You get the same probability after all, okay? But sometimes we don't want to take the measurement of every single qubit. Sometimes in the quantum computing and quantum error correction, we want to take a measurement on specific qubit, and intentionally, because it will collapse the rest of the qubit into certain state, then we're going to use that collapsed state on the rest of the qubit to do some more computation and so on. But therefore, we're not always we're going to work in the superposed state, we need to know what will be the remaining quantum state for the remaining qubit after taking the measurement on the specific qubits. So that makes sense? Okay. So now it's interesting statement. So let's talk about the entanglement. The definition is simple. The quantum state is called entangled because when we have a non-tensor product between single qubit states. So if you take, let's say, phi1 tensor phi0, it's a 1 qubit state for each case. Then it simply means that you physically put together two quantum material which are in a quantum state of phi0 and phi1. So you can just separate apart these two quantum states. So there's nothing going on here. But sometimes you cannot write your quantum state, multi-qubit state, into a tensor product of the separate states. So for example, if you have a state like this, so there are 4 states. So for example, if you take this one, there's no way you can write it as a tensor product of 2 qubits. Okay? So what I'm saying here is that it's not a sum of tensor product. The entangled state is that something that you can write as single tensor product, okay? Not some linear combination of tensor product, okay? So you cannot write this state as a single tensor product, or nor for all the other states. And same thing for this. So this is the 3 qubit state. You cannot write it as a tensor product of 3 qubits. So this is called the entangled state, and these are the typical example of entangled state. And the picture in here on the right is the picture I took from the drama called The Three-Body Problem. And anyone watched The Three-Body Problem? So there is a siphon, right? There's a computer as small as an atom, and the computer is entangled. And there are 2 computers. There you can see that actually there are 4, but anyway, 2 computers as small as atom are entangled so that they send one to Earth and they keep one from themselves. So there's an alien called a what is it called? 3-body and something like that. And they are, they have technology that can make a computer. They are quantum computer. And they made 2 computers and make the two quantum computer entangled each other. So they send one to the Earth and they keep the other. And then since they are entangled, the drama says that the information can be traveled instantly, so it travels faster than the light, and so on. The story goes on there. But actually, that doesn't make sense. It's a nonsense, but I'll tell you the story here. So, there is a when the quantum mechanics, quantum theory appeared, there is a debate about how to interpret the quantum mechanics or quantum theory. So the Einstein argued that if you see something, it should be there. It's basically, if I write it if I say it in a most basic words, it's something like, if you see something, it should be there, even if I don't see it, right? So if I see, like in the chair at the desk like this one, then even if I don't see the desk should be here. That's the realism. So if I measured 1 after taking a measurement on the qubit state, then the 1 should be there, even if I didn't took the measurement. That's the basic concept of the realism. It says basically there is some governing property of that material that if I took the measurement, it will turn out to be 1. So it should be there even if I took the measurement. The hidden variable or hidden property of that state must be there even if I don't took the measurement. It's only after I measurement that property or hidden variable manifests itself as an outcome. But that's not the way you should think when you're talking about the quantum state. So think about this example. Now these are the fully entangled state of 3 qubits. Now suppose that I got it. Actually, there is quantum gates, the series of quantum gates that actually you can produce this state. Anyway, so suppose I got this one, and then suppose I apply Hadamard gate on pair of qubits. So there are 3 qubits, but I only take 2 of them. There are 3 choices of the 3 ways to choose 2 out of 3, and take the Hadamard gate. So if I take the Hadamard gate on, apply the Hadamard gate on qubit 1 and qubit 2, so for example these two, so then what happens is I'll do the calculation with you. So what happens is it's plus 0 minus 0, and you get plus 1 and minus 1. So now let's split it into the base state. So plus 1 is now split it into 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 0, right? Plus gives you all the possible choices with the same coefficient plus signs. And let's take the minus of minus. Now minus gives you 0, 0, 1, 1, 0, but 1, 0, 0, 0, 1, 0. Okay? And then let's take a plus minus. So plus minus gives you 0, 0, 1, 1, 0, 1. Now take the what is it? 1, 0, 1 minus 1, 1, 1, right? And then let's take minus plus. Minus plus gives you 0, 0, 1, 1, 0, 1, minus 1, 0, 1. Okay, and then minus 1, 1, 1. Okay. Oh, I think I did twice. I did compute this twice. So this is 0, 1, 1, and actually it's a minus sign here. Okay. So these are all the states, but there are cancellation. So I can cancel out these two. Okay, how about 0, 1, 0? Where is 0, 1, 0? I have twice of these. So I keep this, and 1, 0, 0 is I have twice of these, okay, and then I have 1, 1, 0 cancel each other, and here I have twice of these, and then I have 1, 0. I have keep this one, and 0, 1, 1. Where is 0, 1, 1? Oh, I counted this twice. Okay, so this one is minus plus. So 0, 1, 1, right? So I have canceled out these two, and I keep these two, right? So 0, 1, 0 is here. There are, how many of them? Here, here, oh, by the way, I forgot to put this coefficient. So the coefficients are 1 over 2 all the places, because each plus and minus has coefficient 1 over square root of 2. So there are 2 of those. So I have 1 over 2, and also I have 1 over 2 over here. So I have 1 over 4 as a coefficient for every state. But now I have 2 of these. So that makes my coefficient for 0, 1, 0 as 1 over 2 here. So I have this. And 1, 0, 0, I keep these 2. So it's here with the coefficient 1 over 2. And 0, 0, 1, 0, 0, 1 have a minus sign, but there are 2. So I keep this. And then I have this one. Oh, there should be cancellation. So let me check. 101 come from here. 101 is plus sign. How about this one? It comes from here. It has 1 minus, okay, so it has a minus here, So this cancels out each other. I have 111 and 111 here goes to here. Okay, so I have 4 states basically. After canceling out all the states, I have 4 states remaining here. So you can do the similar thing here. Okay. So how about I'll give you some time to do the similar calculation as I did for this case. How about you fill in this case? So then let me know after do the calculation. So let me save time. So how about these group do this one, H2, H0. So the people on this side do the third part, H0, H1. Okay. In trouble? Okay.
I can't remember what was the other word.
Hadamard? Hadamard makes 0 into plus, 1 into minus. Do you know what plus and minus mean? A little bit. Plus is sum of 0 and 1. Minus 0 minus 1. Okay. Plus 1, yes. Minus 1, yes. You have problem? Yes. So plus is 0 plus 1, minus is 0 minus 1. So you can distribute 0 and 1. Done? Okay. So you can group them together and write the answer here. Oh, you're doing this one. Okay. Oh, okay, I have it. Okay. Anyone done the calculation? Are you done? Okay. So let's check. So can you call the quantum states from beginning here? Yes. This part. 0, 0, 1 plus 1, 0, 0 minus 0, 1, 0, 1, 1, 1. Okay. Yeah, how about the third one? Anyone done the calculation? How about can you 0, 0, 1, 0, 1, 0, 1, 0, 0 plus 1, 1, 1. Okay. So did you get the same thing? Everyone? Okay, so I think it's right. Okay, so well, that was an exercise. It's not the main point. So what's the main point? Now let's try to think about this situation this way. I'm going to assume my variable x0, x1, and x2 made the measurement outcome after take the measurement on each qubit. So x0 is going to be the outcome after taking measurement on qubit 0 and so on. Now, and if I took the Hadamard gate on each qubit and then take the measurement outcome will be stored in the x0h, x1h, and x2h. Okay, so that's just a variable that I'm going to store as a store there. So it's either 0 or 1. Okay, so let's look at the equation here. Okay, so after I took the measurement, there are several different possible choices of x1, x0, x1, and x2. So for example, if I didn't took any Hadamard gate, as in here, x0, x1, x2, could be 0, 0, 0, 0, 1, 1, or 1, 1, 0, or 1, 0, 1. There are only 4 possible choices for pair of x0, x1, x2, right? So if you add these numbers as a Boolean number, then these are always zero, because in any of these 4 cases, there are either none of 1 or 2 ones, right? If you add them up, then you always get 0 as a Boolean summation. So that's what it says. So it's not just simple addition, it's a Boolean addition. Now, suppose that you applied Hadamard gate on qubit 1 and qubit 2. That's the case when you get this one, and then you take the measurement, then it's either 0, 1, 0, and so on. So if you take the Boolean sum of all the outcome, then you get always 1, because it's either 1, 1 or 3, 1, right? And same thing for other cases. If you take Hadamard gate on 2 qubits and then take the measurement outcome is always summed up to 1. That's what this 3 equation says. Okay? Now, the weird thing is, let's try to add side by side. So how many x0 are there? 2. How many x0h are there? 2. So you can always pair this up, right? So no matter what your x0 is, if there are 2, then if you add all of this, then it always be 0. Right? The left-hand side is 0. How about the right-hand side? 1. You have this weird contradiction. You have this contradiction. So what is wrong here? So this is the problem. This is the core of the problem that bothered Einstein and everyone else who disagreed with quantum computing, quantum mechanics in like almost like mid 20th century. So I'll think about this for a moment and then discuss with your friends next to you to think about what is the reason, what is going wrong in this case. So apparently there is an assumption when you drive this conclusion, the arithmetic assumption. It's a basic assumption in algebra. And that assumption probably not working because it gives you a contradiction. So what is that assumption? Hmm? Okay, so partially right. So can you elaborate a little bit more? Can you think about how to elaborate a little bit more about your idea? So anyone else?
Because I can't separate.
Psi? Uh-huh. Psi can't do what? Psi 3 cannot do separate into 3 qubit. I mean tensor product of 3 qubit. Yes, that's true. And then what's the next? Okay, if it doesn't work, then I mean, I simply did the same. I simply did the addition, right? So there are some assumption in the addition that we probably forgot about for a long time because it's so obvious. -1? Oh, because this is a Boolean algebra. -1 is 1. So I just said it, but we have 2x0. We are adding x0 as if they're the same, right? x0 are the same variable, right? So it becomes 2x0. So no matter what x0 is, it's either 0 or 1, so you get 2x0 is always 0. That's why we got the conclusion on the left is 0, right? Can you imagine it? Can you imagine that this assumption that x0 on the first equation and x0 on the second equation is not the same x0? They're not the same x0. The contradiction is because we assume that these x0s are the same, right? Now, but that's a weird thing because you see, I didn't do any. So if you compare the first equation and second equation, only difference is whether I applied Hadamard on qubit 1 and 2. I didn't do anything on qubit 0, right? So it's physically separated. Qubit 0 is separated from qubit 1 and qubit 2. If I don't do anything on qubit 0, there's nothing changed in here. There's no remote connection between these three qubits. It's only my decision whether I apply Hadamard on qubit 1 and qubit 2. So you can imagine that whatever I observe on the qubit 0, I will get the same thing, whether or not I apply the Hadamard on the rest of the qubit. So it's reasonable to assume that these x0s are the same. However, in quantum computing, quantum mechanics, they are not the same x0. So probably the problem is there is no such thing as x0. You cannot imagine your outcome as a single variable. That's what causes the contradiction. That's called a hidden variable. Like if you observe something x0, it's something internally programmed into the qubit state that if I take the measurement, I would observe some x0. That's called a hidden variable. But in the quantum state, you cannot assume such hidden variable. That's what makes the problem. You cannot identify quantum state as a value that you can identify or manipulate as a number. It's just state that is represented by a vector. There's no value at all, okay? No value as something related to the classical bits. Another way you can think of this is, okay, so let's say, as I said, if you take a measurement, the quantum state collapse. It's gone. You're not gonna get you're not gonna retrieve the same quantum state ever. It's gone, right? So what I'm gonna do is, okay, I'm gonna try to prepare the same quantum state as in this psi state, phi3 here, many of them, and then try to do the same experience over and over, whether I take the phi3 alone or I take the Hadamard gate on 2 of these qubits and then take the measurement. And what the problem is that, okay, no matter how quantum quantum states that you prepare, they are all different in principle. They're not the same. They're not cloned itself, okay? So therefore, you cannot expect the measurement outcome x0 on one experiment is same as the x0 on the second experiment, okay? So they are all different x0. You cannot assume they're the same. But let's imagine a little bit more weird situation. Let's say I have a time machine, okay? I prepared the quantum state with this qubit state, and then I took the measurement without having Hadamard gate, and then I have a result, and I take the time machine, and then going back before I take the measurement, and then now I have the same quantum state. Now I'm going to apply the Hadamard on qubit 1 and qubit 2, then take the measurement. If I do it over and over, let me say it like 4 times, taking a Hadamard on all different choices of qubit, I still get this contradiction, right? So the problem in that case is that even if I took the time machine and going back in time to get the same quantum state, they're not the same, right? So suppose that imagine the quantum outcome, the measurement outcome is something like you spot the electronic spin of the electronic. So it's actually how the quantum computer works in hardware. When you have a quantum material, you want to identify the spin direction of the electron. So it's either spin up or spin down after you take the measurement. Now, when you try to imagine how you observe the spin direction of electron, as if it's electron floating around the atom, and then at this moment in the right place and right time, you will get the electron at the spin up position. So if you're going back in time, assuming that you take the measurement at the exactly same time, at the exactly same circumstance, everything is same, but the quantum mechanic, like in this example, says that you will not get the same outcome. Still, you have a 50-50 chance. So it's not about like nothing similar to the classical mechanics. In classical mechanics assumes that if you have the same conditions, same environment, everything is the same, you should have always the same outcome, right? That's the classical mechanics. But quantum mechanics doesn't say that. Everything is probabilistic, okay? So there are many ways to explain this, but anyway, none of them actually feels right in our conscience. But anyway, if you take this anything about this quantum computing, not as a real something that you can feel in a physically real, but if you just take it as a mathematical statement, like this is the vector that describes the state, then nothing is wrong. Nothing is weird. Okay, but the problem arises when you try to think of it as a real phenomenon, like a physical phenomenon. So there's a gap. So now you have to do the computation purely in a mathematical way, but in real life there is an actual quantum computer that you imagine that this is somehow working in a certain way, but none of the intuitive idea works. But anyway, that's how it works. That's how quantum world works. So you have to accept this. So here's another situation here. So I want you to compute all this Hadamard, all this quantum state after applying the Hadamard gate here. And then we're going to talk about the similar paradox here. So first, we have this all four state, a little bit different probability of the observation outcome. But let's see what happens after taking the Hadamard gate. So if I take the Hadamard gate on 0 and 1, this becomes 3 plus plus, plus minus, minus plus, and minus minus. So it's 0, 0, 0, 1, 1, 0, 1, 1, and 0, 0, 1, 0, minus 1, 1, 0, 1 first, 0, 1, and minus 1, 1. And then here I get 0, 0, 0, 1, minus 1, 0, minus 1, 1. And here we have 0, 0, 1, 1, minus 0, 1, minus 1, 0. So we have 3 of these. So I'm going to compute. Oh, I have a minus sign here. So it's a minus, minus, plus, plus here. So how many zeros we have? 0, 0. So this becomes 4, right? 4, 0, 0. And then how many 0 1s here. 1, 2, and 0 1s here. So we have 4, 4, 0, 1. And then, let's see, 1, 0, here, 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 1, 0. We have plus. So we have 4. Again, 4. So, and then how many 1 1s here? Minus, minus, minus. 3 minus and 1 plus. 3 plus. So we got raise this. So we have 1 over 2 of this as coefficient, And okay, so maybe get rid of this 1 over square root of 2. And let's try to compute this. Okay, so 2 cancel out with this 4. So I get 2, 2, 2. So 12 here canceled with this 2. So I get 1 over 3 of 0, 0, 0, 1, and 1, 0, and so on. So you can do the similar computation for the rest of the parts. What we are going to talk about here is, okay, here's a situation, similar situation. Originally, I had this situation. This is quantum state. But I'm going to decide, I'm going to flip the coin whether I apply Hadamard gate on qubit 0 or qubit 1 or both. Okay? So before I flip the coin, if I take the measurement, then there are 1 over 12 chances, okay, 1 over 12 probability of observing these 3 states. Okay? So that means I still have chance to observe 1, 1. Okay? But let's see. If I applied Hadamard gate on both of this qubit, what happened is I don't have 1, 1 state anymore. Okay? So mathematically, nothing is wrong. So because it's 1, 1 is gone, that's why you don't observe 1, 1. But if you think about this as a with something similar to the hidden variable idea, that if you had a chance to observe 1, 1, that means the quantum state has some portion of this quantum state, whatever that is, that could turn out to be 1, 1. Then even if you take the Hadamard gate on both qubit, 1 will turn out to be plus, minus and minus, minus and minus, when you take the Hadamard gate on both qubits. And minus minus is some superposed state of 0, 0, 0, 1, 1, 0, and 1, 1 with some coefficient. So therefore, you still think that there is a chance to observe 1, 1. Or you also think that, okay, so even if I have chances to observe these other two, they still have this 1, 1 state after taking the Hadamard. So this is plus minus and minus plus. So therefore, if there is some part of the quantum state that appears to be one of these states, then even if I take the Hadamard, I still have to have a chance to observe 1, 1. But that does not happen because this 1, 1 is disappear after it had taken the Hadamard. So if this contradiction doesn't make sense to you, that's fine. Don't try to make sense of this contradiction. But if it doesn't make sense, I mean, if this contradiction makes sense, then now you have to drop the idea of the realism, that the quantum state has certain aspect of giving you the outcome of these quantum state. If you assume that, then this contradiction is going to bother you a lot. But sometimes, in my case, it's my personal experience, I saw this example in a book, and then I did understand what the contradiction says. Simply, it's hard to understand the contradiction itself. But it's not necessary. I mean, you don't need to understand this contradiction because it's not something that you should understand. But sometimes this helps to change your perspective on how to recognize your quantum state. Okay, so whenever you, so it's something like if you see the expression like this one, it's not that you have 0, 0 state, 1, 0, 1 state, 1, 0 state, 1, 1 state mixed together in a quantum system and with some probability. And when you try the measurement, you something like you pick one of these out of the box randomly. It's not like that. Okay. So if you have this idea, you have to get rid of that idea because that will not going to happen. It will make this contradiction like this one. Okay? So best way to understand quantum state is it's just a vector. It's not a real, it's not something that you can have in your hand as a real object. It's just a vector state. And whenever you take the measurement to see what really is, it's going to collapse to your observation and it will going to give the outcome with the probability, with some probability, but that probability doesn't tell you anything about the quantum state. That's just the probability. It's just a estimate of how many observation you will get if you try to copy the process of measurement many, many times. But it doesn't tell you anything about the specific quantum state alone. Okay. So what else we have here? Okay, one more thing. So it's called the spooky action at distance. Maybe some of us are familiar with also what bothered Einstein. Suppose that you have quantum state, Bell state like this. Now why the drama three-body problem, it's a nonsense. So it says, okay, so they entangled this quantum computer, the highly sophisticated and highly, what is called, the size of the data that it contains is ridiculously large. And they entangled these two computers together, and then they separated it apart. So it's as small as atom and almost zero mass. So it sent it to the Earth as fast as a light speed. So it arrived at the Earth first, and then the alien arrived to the Earth. And they could communicate at a instant speed. So what they did, so the idea comes from this entangled state. So you have two quantum states entangled together. You have a 0, 0 plus 1, 1. You separate this quantum object apart like a few light years away. And then let's say here's an Alice and Bob in a light year distance. Alice takes one of the qubit, Bob takes the other qubit. They are fully entangled. If Alice takes the measurement and observes 0, Bob will always observe 0, right? Because if you take a measurement on 0, it kills the other. So Bob will always just observe 0. Now, if you think this is some transformation of information, that somehow the action of the measurement of Alice gives the information to the quantum qubit that Bob has, so that this qubit will always give the measurement outcome as 0. That doesn't make sense because the information is transferred instantly faster than the light speed. That's the violation of the special relativity. So that's not how you should explain the quantum entanglement. So why it's wrong? Why is that idea wrong? It's because you're assuming that this entangled state is somehow mixture of these 0, 0 and 1, 1. So if you pick up this, so if you imagine that this is a black box that you don't know what to choose, but if you pick 0, 0, then you kill the other one. So there's a box, Alice and Bob has two boxes that are somehow connected to each other. If you pick this one, that one is already immediately chosen. That's not how you think, because it assumes that it's somehow there is a hidden variable that determines the measurement outcome as 0, 0, or 1, 1. It's easier if you think this way. There's no such value, there's no such variable that contains the outcome, that represents an outcome of the measurement. There is no such thing. So if you start to think about variables, some sort of a variable x that Alice has and Bob has a variable y, and somehow this variable x determines the value of variable y, that's the contradiction. That's where contradiction begins. There's no such variable that can represent the measurement outcome of a quantum state. So now you see why the drama is nonsense, because that and three-body problem. I'm not saying that drama is bad. I love the drama, but the way they explain is that, okay, if I do something on the Earth side and now change the variable on this side of a qubit, then the drama assumes that because of it's entangled, then it will change the variable on the other side of the qubit, the variable y. It doesn't work that way. There's no such thing x and y that contains the information about the qubit.
원하는 값을 뽑는 게 아니라 그냥 2분의 1 확률로 그냥 관측하는 거기 때문에 정보를 전달하는 게 아니라.
No, yes, basically, yes, you're right. So it's not the transformation of information. It's not about the transformation of information. Well, still you can say, okay, well, still Bob has, deterministic outcome because of the Alice's action, right? Well, think of it this way. If Alice and Bob are close to each other, Alice took the measurement first, and Bob knows it, and Bob knows what Alice got, then the information already delivered, right? So if you want to know whether the information of the information of the quantum that Alice has been delivered to the information on the qubit that Bob has, then you have to have somehow ways to deliver the measurement outcome of Alice faster than the light to the Bob, so that Bob knows before, instantly, or at least faster than the light speed, that what the Alice's measurement outcome is. So there's no way you can actually prove that information is delivered way faster than the light. So because there's no means of delivering the information faster than the light. So, I mean, practically it's impossible to, even if you assume that this is as a somehow information transformation, there's no way you can check whether this is delivered or transported faster than the light. And yeah, even if you don't assume that, if you think of this as a hidden, somewhere there is a hidden variable, then it already doesn't make sense with prior examples that I showed you. Okay, so that's that. And so any questions or anyone wants to clarify any part? So how do you make an entangled state? It's easy. Let's make an entangled state. So it's not a science fiction. It's really, it's a state that really exists. Not sure whether I mentioned this before. So here we have 2 qubits. So I'm going to take a Hadamard on here. Oh, sorry, not this one. And then take a CNOT gate. And what's going to be the quantum state at this moment here? Right. So here I'm going to, let's see, separate it into 3 pieces. So here we have first state. Here we have second state. Third state. So the first state is 0, tensor 0. But in the second state, I applied Hadamard on the 0, so it's going to be 0 plus 1/2 of 0, 0, 1, 0, 1. And then I apply C naught, taking the 0's qubit as a control qubit, and 1 is the target qubit. So based on the state of controlled qubit, so this is the controlled qubit state, okay? So since it's 1 on this side, it will apply X gate to the qubit 1, okay? So this makes 0, 0 plus 1, 1. Now you have entangled. 2 entangled state of 2 qubit state. Okay, let's try to think about how you could make another quantum state. So let's have an example, since we have time. So let's try to make this state. Make 0, 1, 1, 0 using X, Z, control X, Hadamard. So try to compose a quantum circuit as I did in here, using XZ, controlled X, and Hadamard to make this entangled state. Your turn. 0 or 1, 0, 0. Okay.
I didn't use it.
Oh, you didn't use yet. Okay. Hadamard is 1, 1. That's a bit weird. 0, 0. Oh, yes, that's right. Right, right. So how about if you want to make this? So basically you can make all 4 Bell states using either, or combination of these 4 gates. So basically this first one is simple, right? 마이너스 0, 1. Where did you apply it? Z. It's hard to compute here. How about the code? Can you see the code? There's can you press this? Press this. No, not that one. Okay, so there is the window you can use for the Qiskit code. So if you use the Qiskit code, it gives you the state vector with the coefficient. But you can check whether it's actually minused. Compute the quantum state. Compute actual quantum state with the hand, and you can see whether it's minused. So anyone got the first one? How do you get this one? How did you get this one? Yes. So here, so 0, 1. So we are assuming whenever you start the circuit, we assume every single qubit is initialized at cat 0. So it's easy. How do you initialize cat 0 state? How do you initialize every qubit into cat 0 state? Simply take the measurement. Take the measurement until you get 0. That makes you cat 0 initialization. Okay? So then you start the circuit. So you said take the Hadamard and then X and then this. Is it right? Okay. Right. So can you see why this is true? So next time we're going to talk about the quantum circuit in more detail, but this is same as this circuit. You can change the gates here. You can change the order of your gates. Do you see why it makes sense? Does it make sense to you? Why it's okay to change the order of the gates in this case? The one reason is X, X is commutable with X itself. That's one reason. And also, applying Hadamard doesn't do anything on the qubit 1. Therefore, it doesn't have to be on here. So you can actually do it in a sequel like this one. So let's see. It's same as this. So you first take the Hadamard and then take the X on the second qubit and then take the controlled X. But now the problem is it okay to switch the controlled X and X gate here? It's allowed because the X gates are on the target qubit. X is applied on the target qubit. So target is a receiver. So it doesn't affect it doesn't matter what the value is after the controlled gate. So I'm simply applying X and X twice or X alone. So there's no difference. But if you have an X gate on the controlled gate, now there's a problem. It changed the result. So be careful on switching the order on that. But here you can change the order. So now there are two different ways to make the same outcome here. And how about this? The third one. How do you make it minus? So you only want to change when the qubit 1 is at the ket 1 state. What kind of gate does that? What kind of gate flips the phase of ket 1? Gate. There are 4 gates we can use here. So Z gate, right? Z gate flips the phase of ket 1 state. So here we want to flip based on the state of ket 1, qubit 1. So therefore I need to apply Z gate on the qubit 1. So the picture would be here, Hadamard. So you can apply X. So basically you first make this qubit and then flips the phase on Z, on the first qubit. Okay. Okay, so next time we're going to talk about how to compose a quantum circuit. There are several identities between quantum circuits. For example, this one is same as this one. And for example, if you take this one, it's same as Hadamard, Z. Well, that's just the one example. There is a many variation to this, this one, and so on. So we're going to talk about this composed quantum circuit, equivalence of quantum circuits and quantum measurement and so on. So after we fix our group, oh, by the way, we don't have class on Wednesday. So on Friday, I'm going to give you the fixed group. So I'm going to follow the basic information you gave me here. So if you have any change on your group member, let me know so that I can put it in the formation. What is it? Where is the group? Okay. So if you have any change on your mind, so let me know. So based on the information you put it in here, I'm going to make a group of 3 or 4 possible. So what you should do is, for the first project, is making a quantum simulator. So you don't have to follow the same format of the Qiskit or the same visualization of the quantum circuit. You can design on your own, but you have to understand how these quantum gates and how quantum states are computed based on the basic concept of quantum operators and quantum state. So at least you have to think what will be the outcome of your project. Are you going to make a graphical interface of quantum simulator, or are you going to make a package that computes some quantum states with the quantum gates, or are you going to make it as something like hardware or design of hardware or so on? So just imagine what will be your outcome will be, and then when I give you the group, then you can discuss your idea with the group member how to make your actual outcome of your first project. Okay, so have a good holiday season and see you on next Friday.